Right now, in these massive steel pressure vessels operating in industrial parks all over the world, chemical engineers are basically fighting a microscopic, invisible war. They're pouring in raw materials, cranking up the heat, manipulating the pressure, doing everything in their power to force nature to give them what they want. But nature doesn't just hand over a finished product.
No, it really doesn't. It fights back. It has this relentless, innate desire to reach a stalemate.
Right, and the weapon that engineers use to understand and ultimately to manipulate that stalemate is actually a single, deceptively simple number. Welcome to the deep dive. We've got an incredible stack of source material today, and we are diving deep into the actual mechanics of chemical equilibrium.
And our goal here isn't just to talk about theories in the abstract. We really want to extract the fundamental machinery of what chemists call the equilibrium constant, which is represented by the symbol Kc.
Kc. Yeah, and I want to pitch this not as a dry math lesson, but really as a mathematical cheat code. It's the defining ratio that tells you exactly where that tug of war is going to settle, right?
Yeah.
So we are going to walk step by step through the actual calculation steps for finding these constants.
Exactly. We're going to look at the specific variables, the concentrations, the physical realities of the molecules themselves, and show exactly how they snap together to create this constant.
So we're going to completely demystify the math behind Kc. We want to show how it's actually just an elegant reflection of physical reality. And along the way, we're going to clarify exactly how one single physical factor, temperature, acts as the undisputed tyrannical ruler of this constant's final value.
It really is the master switch. I think people often look at chemical equations and they just see like an abstract logic puzzle.
Yeah.
But my focus today is to ground this in reality for you. We want to understand why the math behaves this way. Because when you understand the physical collision of the molecules, the algebra just becomes a natural description of that violence.
I love that phrase, the algebra of violence. Let's get right into it then. Before we calculate anything or look at any laboratory data, we have to establish what this equilibrium constant actually is. So I was going through the defining text in our source material, and I have to say, the formal definition of Kc is one of those incredibly dense, mathematically rigorous sentences that can just make your eyes glaze over.
Oh, absolutely. Textbooks have a habit of doing that.
Right. I mean, it defines the equilibrium constant as a ratio. Specifically, quote, the product of the concentration of products raised to the power of coefficient to the product of concentration of reactants raised to the power of coefficient, end quote.
It's a very precise sentence, and, well, it has to be. But let's strip away that linguistic density. When the text says ratio, it's really just establishing a fundamental relationship. Products over reactants.
Okay, let's unpack this. So it's basically a simple fraction.
Exactly. The substances you are creating, the products, they sit on top of the equation in the numerator, and the ingredients you started with, the reactants, they sit on the bottom in the denominator.
Right. But the language plays a bit of a trick on you here because it uses the word product in two totally different contexts within the same breath. Like, it asks for the product of the concentration of products.
Yes. And that is a classic scientific pitfall for students. The first product is a mathematical instruction. It just means you multiply the values together. But the second product is chemical. It refers to the actual newly formed molecules on the right side of your reaction arrow.
Oh, I see. So if my reaction creates two different things, let's say I'm making ammonia and water, I don't add their amounts together on top of my fraction. I have to multiply the concentration of ammonia by the concentration of water.
Precisely. You multiply them. And you do the exact same thing on the bottom with your ingredients. Multiplication is the key here because we are dealing with simultaneous probabilities, which we'll get to in a second. But then the definition introduces that crucial modifier raised to the power of the coefficient.
Okay, yeah. This is where the formula turns from a basic ratio into something highly specific. The coefficient is just that big number sitting in front of a molecule in the balanced equation, right? Like a recipe. If I need 3 hydrogens, there's a big 3 sitting there.
Right, the stoichiometric coefficient.
But when we actually calculate Kc, that big 3 doesn't stay a multiplier. It leaps up and becomes an exponent. We cube it. Why on earth does the physical recipe translate into an exponential power in the math?
This is where it gets absolutely fascinating, and it goes back to what I just mentioned about probability. Think about what a chemical reaction actually is on a microscopic level. It's not magic. It's literal molecules physically crashing into each other.
Like a demolition derby in a beaker.
Exactly. A microscopic demolition derby. They have to crash with enough force and at the perfect angle to break their old bonds and form new ones. Now, if one molecule of A needs to hit one molecule of B, the chance of that happening depends on how crowded the beaker is, their concentrations.
Makes sense.
Yeah.
More crowded, more crashes.
Right. But what if the recipe demands that 3 molecules of hydrogen must react with 1 molecule of nitrogen all at the exact same time?
Oh, wow. The odds of 3 hydrogens and 1 nitrogen all colliding perfectly at the exact same millisecond, it must be astronomically lower.
They are. It's incredibly unlikely. Mathematically, to find the probability of multiple independent events happening at once, you have to multiply their individual probabilities together. So if hydrogen needs to be there, and another hydrogen needs to be there, and a third hydrogen needs to be there, you are multiplying the concentration of hydrogen by the concentration of hydrogen by the concentration of hydrogen.
Wait, hydrogen times hydrogen times hydrogen? That is literally hydrogen cubed.
There it is. The coefficient in the balanced equation becomes an exponent in the Kc expression because it perfectly maps the geometric probability of those specific molecular collisions happening in 3-dimensional space. The math is just a mirror of the physical chaos.
That completely changes how I view these formulas.
Yeah.
I mean, it's not just an arbitrary rule some chemist invented just to make things hard. It's a statistical necessity.
Exactly. It's rooted in the physical reality of the active mass, which, by the way, is a specific phrase the source notes emphasize.
Yeah, Test Yourself 9.2 asks how active mass is represented. Right, and it's represented by those square brackets.
Yes. The square brackets are the universal shorthand for active mass, which is just concentration. It's usually measured in moles per cubic decimeter. When you see a chemical symbol inside square brackets, like an H2 inside brackets, you are looking at its active mass. You're asking, how tightly packed are those hydrogen molecules in that specific volume of space?
Which directly dictates how likely they are to crash into something. Like if we look at the specific rate equations provided in the text for the Haber process, that's the reaction-making ammonia, this all just clicks together perfectly.
It really does. Because the speed of the forward reaction, which they label as RF, is directly tied to the concentration of nitrogen multiplied by the concentration of hydrogen cubed.
And then conversely, the speed of the reverse reaction, R, which is the ammonia breaking back apart, is tied to the concentration of ammonia squared, because 2 molecules of ammonia are involved in that specific breakdown step.
Right, so we have these 2 speeds, the forward assembly line and the reverse dismantling line. Now, at the very beginning, you only have raw ingredients. So the forward line is racing, and the reverse line is completely stopped because there's no product to dismantle yet.
Like unbaking a cake. But you haven't baked the cake yet, so you can't unbake it.
That's a great analogy. But as soon as the first few molecules of ammonia are formed, the reverse reaction kicks in. The ammonia starts breaking apart. And as those raw ingredients get used up, the forward reaction slows down.
And inevitably, those 2 speeds are going to cross paths.
They will perfectly align. The exact millisecond the forward speed, RF, equals the reverse speed, RR. The system has achieved equilibrium. Macroscopically, the world looks completely still. The amounts of nitrogen, hydrogen, and ammonia in the tank just stop changing.
But microscopically, it is still a raging storm. For every million molecules of ammonia formed, a million are ripped apart.
Exactly. And if you take the mathematical constants governing those 2 equal speeds, and you divide the forward constant by the reverse constant, you give birth to Kc. The equilibrium constant, it is the literal scoreboard of that stalemate.
It is. Which brings us to the most counterintuitive, heavily emphasized rule in the entire source document regarding how this scoreboard operates. We need to talk about what actually controls that final score.
You're talking about the golden rule of initial concentrations. I know a lot of people struggle with this concept.
I certainly did. I read this part of the notes several times because it feels like a paradox. The text explicitly states that the value of Kc does not depend on the initial concentrations of the reactants in the products.
It's a massive conceptual hurdle.
Right. Because logically, as a listener, you think, wait, the entire formula for Kc is literally built out of concentration numbers. Bracket this, bracket that. It's a fraction made of concentrations. How can the final value of that fraction not depend on how much stuff you start with?
Well, we have to separate the concept of inventory from the concept of a ratio. What's fascinating here is that the Kc is a designated relationship that the system is physically compelled to achieve.
Walk me through that. How does a beaker of chemicals know what ratio to hit?
Okay, let's strip away the chemistry for a second. Think about a simple mathematical ratio, like 1 to 2. If I give you 10 blue marbles and 20 red marbles, the ratio is 10 over 20, which reduces to 0.5.
Okay, simple enough.
Now, what if I dump 5,000 blue marbles and 10,000 red marbles on your desk? The absolute numbers, your initial amounts, are wildly different, but the fundamental relationship between them, 5,000 over 10,000, still reduces to the exact same constant, 0.5.
Oh, I see. The sheer volume changed, but the proportion remained identical.
Exactly. In a reversible chemical reaction, the Kc is that unyielding proportion. It is a mathematical destiny determined by the specific nature of the molecules involved. If you start a reaction by dumping in a swimming pool's worth of reactants, the system doesn't panic. The forward reaction will just run extremely fast, generating a massive amount of product until the sheer density of that product forces the reverse reaction to catch up.
And it will just keep shifting, reacting back and forth, speeding up, slowing down, eating up reactants and spitting out products, purely to ensure that fraction gets back to the correct Kc value.
It will do whatever it takes to satisfy that ratio. The initial inventory is irrelevant to the final proportional balance.
That is wild to think about. It's like the molecules are performing calculus in real time just to ensure the universe's ledgers are perfectly balanced. But, as our notes emphatically point out, there is one thing, and literally only one thing, that can rewrite that ledger. Yes, temperature. This is a major focus for us today. The text states, quite definitively, quote, "The value of Kc depends only on temperature," end quote. So if initial concentrations can't change the ratio, why does temperature have this exclusive godlike power over the equilibrium constant?
To understand this, we have to stop thinking of temperature as just a number on a thermometer. We have to start thinking about it as what it truly is: kinetic energy. It is the raw velocity and violence of the molecules in the system.
So hotter means the molecules are vibrating faster, they're flying around faster, and they're crashing into each other with much more force.
Precisely. Now remember our two assembly lines, the
Yeah.
forward reaction and the reverse reaction. Those two processes are almost never energetically symmetrical. One direction of the reaction might require an injection of heat to force the molecules apart. That's an endothermic process.
Okay, and the other direction?
The other direction, snapping the molecules together, might actually release heat into the environment. That's an exothermic process.
So they have entirely different relationships with heat. One feeds on it, and the other tries to get rid of it.
Yes. So imagine our system is sitting at a comfortable room temperature, perfectly balanced at its specific Kc ratio. What happens if you suddenly put a blowtorch to the flask and flood the entire system with intense thermal energy?
Well, the reaction that wants heat, the endothermic one, is suddenly going to hit the gas pedal.
Right.
It has all the fuel it could ever ask for.
Exactly. And the other reaction, the one trying to release heat, is suddenly fighting an uphill battle against this hot environment.
So the two speeds, RF and RR, are no longer equal. You've completely broken the stalemate.
You've added a massive tailwind to one direction and a headwind to the other. The system will scramble, shifting concentrations wildly. Now, eventually, it will find a new stalemate. The speeds will eventually equalize again at the new temperature. But because the underlying energetic landscape was fundamentally warped by the heat, the final amounts of products and reactants they settle at will be completely different.
Meaning, when you divide those new product numbers by the new reactant numbers, you get a completely different number.
A brand new Kc. If the constant was 80 at room temperature, heating it up might permanently shift the constant down to 40, or up to 200, depending entirely on which direction absorbed the heat. Temperature is the only thing that changes the rules of the game, because it's the only thing that changes the energy required to play.
That makes perfect sense. It's not just a variable, it's the environment itself. Keep the temperature steady, the Kc is locked in stone. Change it, and you change the fundamental ratio of the universe for that specific reaction.
Exactly.
Well, to prove that this ratio actually works, I want to transition from the theory of the scoreboard into actually running the math, step by step. The source material provides some excellent laboratory data sets to demonstrate this, starting with problem 9.1.
Let's walk through them. Seeing the numbers crystallize the theory is really helpful.
Okay, so I was looking at the first scenario provided, we'll call it the hydrogen iodide experiment. The setup is a sealed flask, and the text specifically notes the temperature right up front, 25 degrees Celsius.
And you should notice that right away. They locked in the temperature. That tells us we are hunting for a fixed, immutable Kc value for that specific thermal state.
Exactly. So at 25 degrees, we have hydrogen gas, H2, and iodine gas, I2, reacting reversibly to form hydrogen iodide, which is HI. So the balanced chemical equation is H2 plus I2, reversible arrows, 2HI.
Okay, let's build the expression first. This is the blueprint for our calculation. Products over reactants.
Right, so our product is HI, And looking at the equation, it has a big coefficient of 2 in front of it. So following our rules of probability and collision we discussed earlier, that 2 becomes an exponent.
Yeah.
Our numerator is the concentration of HI squared, bracket HI bracket squared.
Perfect. Now the denominator are reactants. We have H2 and I2. Neither of them has a visible number in front of them in the balanced equation, which means they're just implied ones.
So they stay to the power of 1. And since it's the mathematical product of the reactants, we multiply them together. The denominator is bracket H2 bracket times bracket I2 bracket.
So our complete algebraic blueprint is Kc equals Hi squared divided by H2 times I2. Now for the empirical data, what concentrations did they actually measure in the lab once the system hit equilibrium?
I've got the readouts here. The equilibrium concentrations are hydrogen is at 0.05 moles per cubic decimeter. Iodine is at 0.06 moles per cubic decimeter.
Right.
And the product, hydrogen iodide, settled at a massive 0.49 moles per cubic decimeter.
So we plug those numbers directly into our blueprint. Let's evaluate the numerator first. The concentration of our product, 0.49 squared.
Okay, I ran these numbers verbally earlier to make sure I had the flow right. Squaring 0.49 gives us 0.2401. So that's the top half of our fraction.
And the bottom half. We multiply the hydrogen by the iodine, 0.05 times 0.06.
Which yields a very small denominator of 0.00030.
Yeah.
So the final step is just dividing our product value by our reactant value. 0.2401 divided by 0.00030. And when you run that, it yields a clean, remarkably even number, exactly 80.
So the equilibrium constant, Kc, for the formation of hydrogen iodide at exactly 25 degrees Celsius is 80.
But here is where the text points out something incredibly subtle, but deeply profound about that number 80. What are the units? I mean, we plugged in all these numbers measured in moles per cubic decimeter, right? So is the answer 80 moles per cubic decimeter?
It is not. And the reason why is a really beautiful piece of mathematical symmetry. The text explicitly states, quote, Kc has no units in reactions with equal number of moles on both sides of the equation.
Let's trace the algebra of the units to see why they vanish. It's like the units are ghosts in the machine undergoing the exact same torture as the numbers.
That's exactly how dimensional analysis works. Look at the numerator. We squared the concentration of Hi. That means we didn't just square the number 0.49, we squared the physical unit itself. The top of our fraction has a dimensional unit of moles per cubic decimeter squared.
Now the bottom. We multiplied hydrogen's concentration by iodine's concentration. So a mole in per cubic decimeter times a mole per cubic decimeter.
And anything multiplied by itself becomes squared, so the denominator is also moles per cubic decimeter squared.
Oh, so you have the exact same dimensional block on the top and the bottom of the fraction. Just like dividing 10 by 10 gives you 1, these units perfectly cancel each other out of existence.
Leaving us with just 80, a pure unitless number.
Think about what that means philosophically. It's kind of like doing a currency exchange between two countries where the exchange rate happens to be exactly 1 to 1. If I trade 100 apple coins for 100 orange coins, the math is 100 divided by 100. The numbers cancel, but the concept of the coin cancels out too. I am left with a pure representation of parity.
That is a really brilliant analogy. The unitless Kc is telling you a story about the symmetry of the reaction space. Because 1 mole of hydrogen and 1 mole of iodine, which is 2 total moles, reacted to form exactly 2 moles of hydrogen iodide, the physical volume of the system was perfectly preserved.
No space was crushed, no space was expanded.
Exactly. Physical dimensions canceled out, leaving only the pure mathematical ratio of the chemical preference.
It's elegant, it's perfect. But chemistry is rarely perfectly symmetrical, which leads directly to my next question. What happens when the literal number of molecules on each side of the equation is imbalanced? What happens when we are actually crushing space?
Then the units survive. And they warp into something very strange. The text provides a perfect scenario to explore this in problem 9.2, moving from hydrogen iodide to a much more industrial process, the synthesis of ammonia.
Ah, the Haber process. We talked about this earlier.
Yeah.
And the very first thing I noticed in this data set is the temperature condition. They aren't running this at a comfortable 25 degrees room temperature.
No. What does the text stipulate?
Quote, for the formation of ammonia by Haber's process at 500 degrees Celsius, end quote.
500 degrees Celsius, extreme blistering heat, which means the Kc value we're about to calculate is going to be governed by a completely different thermodynamic reality than our last example. We're reinforcing the point that temperature dictates the specific reactions.
Right, a whole new destiny. Let's look at the equation. Nitrogen gas plus hydrogen gas yields ammonia. N2 plus 3H2, reversible arrows 2NH3.
Stop right there and look at the physical geometry of that recipe. On the left side, the reactant side, we have 1 molecule of nitrogen and 3 molecules of hydrogen. That is 4 distinct units of gas.
But on the right side, the product side, we only have 2 molecules of ammonia.
We have 4 separate molecules violently slamming together and fusing into just 2 molecules. We are fundamentally having the physical space required by the gas. It is a massive spatial compression.
And that compression is going to wreak absolute havoc on our units. Here's where it gets really interesting. Let's build the expression. Products over reactants. Numerator is our product, ammonia. Coefficient is 2, so it's bracket NH3, bracket squared.
And the denominator?
Reactants. Nitrogen is to the power of 1. Hydrogen has a coefficient of 3, so it's cubed. The denominator is N2 times H2 cubed. So our blueprint is Kc equals NH3 squared divided by N2 times H2 cubed.
Now the lab data. What are the equilibrium concentrations at 500 degrees?
The nitrogen is sitting at 0.602. Hydrogen is at 0.420. And the product ammonia is at 0.113.
This is where the exponential math really shows its teeth. Let's look at that denominator, specifically the hydrogen term. We have to cube the concentration of 0.420.
I calculated this out earlier, and it really blew my mind how fast the number shrinks. When you cube a number smaller than 1, it plummets. 0.420 times 0.420 times 0.420 drops all the way down to roughly 0.074.
Think about the physical reality of that. Because the reaction requires 3 hydrogens to collide simultaneously, the mathematical probability of that happening drops exponentially compared to a simple one-to-one collision. That plummeting number reflects exactly how much harder it is for the reaction to proceed.
That is incredible. Okay, so we take that tiny 0.074 and multiply it by the nitrogen concentration, which was 0.602 to finish the denominator, giving us about 0.0446.
And the numerator, the ammonia concentration, 0.113 squared.
That drops down to about 0.0127. So we divide our tiny product number by our tiny reactant number, 0.0127, divided by 0.0446, and we get a final Kc value of 0.286.
The numerical constant at 500 degrees is 0.286. But here is where we must face the unit gymnastics. Let's slowly trace the dimensional units through that exact same algebraic meat grinder.
All right, let's look at the numerator. We squared the ammonia concentration. So the top of our fraction has units of moles per cubic decimeter, all squared, a power of 2.
Now the denominator. We had nitrogen to the power of 1, and we had hydrogen cubed, a power of 3. When you multiply those dimensions together, you add the exponents. 1 plus 3 is 4.
So the bottom of the fraction carries a massive unit of moles per cubic decimeter to the 4th power.
You have a power of 2 on top and a power of 4 on the bottom. According to the algebraic rules of dividing exponents, you subtract the bottom from the top. 2 minus 4.
Which gives us a -2. So the units don't cancel out cleanly like they did with the hydrogen iodide. They invert.
Go ahead.
We're left with moles per cubic decimeter, all raised to the -2.
And when you distribute that -2 exponent across the terms inside, the mole becomes mole to the -2. And the decimeter to the -3 times -2 is +6, so it becomes decimeter to the 6.
So the final, fully written answer for the constant is Kc equals 0.286 mole to the -2 decimeter to the 6. I have to admit, when I first saw this, I kind of hated it. It feels completely messy. Is it common for a quote-unquote constant to have constantly shifting units depending on the specific equation?
It is a unique quirk of chemistry, and I understand the instinct to want a clean, standardized unit. But what you are looking at is actually deeply precise. The numerical value MASH 0.286 is constant for that temperature. But the type of unit is entirely dependent on the specific chemical recipe. The shape of the unit is a fingerprint of the reaction's geometry.
A fingerprint of the geometry. Elaborate on that.
Remember how we established that 4 molecules were cramming together to form 2 molecules? The mole to the -2, decimeter to the 6th unit, is the mathematical scar left over from that physical compression. It is telling any chemist who reads it, hey, this constant belongs to a system where the physical volume of the active particles is condensing. The unit isn't just a label, it's a structural description of the reaction itself.
That completely flips my perspective. It's not a messy unit, it's a highly descriptive one.
Yeah.
Okay, so we've successfully calculated the KIC value twice now. We walked through calculating the constant from both a perfectly symmetrical reaction and a highly compressed one. We've proven the blueprint works. But what if we reverse engineer the entire math problem?
You mean if we already know the destination, but we've lost some of the math?
Exactly. Like, what if we already know the Kc and are missing a concentration? The source material introduces problem 9.3 to test our algebra skills in exactly this way. It involves phosphorus trichloride -PCl3 reacting with chlorine gas, Cl2, to form phosphorus pentachloride, PCl5. So PCl3 plus Cl2 goes to PCl5.
Let's check the symmetry of that reaction immediately.
1 molecule of PCl3 plus 1 molecule of Cl2 yields 1 molecule of PCl5. So we have 2 moles of gas reacting to form 1 mole of gas. It's another compression, but a slightly different ratio.
Right, 2 to 1. And what data does the lab provide us this time?
Well, this is the twist. They just hand us the equilibrium constant right up front. At this particular temperature, the Kc is 0.13 mole to the -1 decimeter cubed.
Notice the unit there, mole to the -1 decimeter cubed. Because we went from a power of 2 on the bottom to a power of 1 on top, 1 minus 2 is -1. The mathematical fingerprint perfectly confirms a 2 to 1 compression.
It's so satisfying to see that work out. So we know the Kc is 0.13, and they gave us the concentrations of the two reactants. Phosphorus trichloride is sitting at 10.0, and chlorine is at 9.0. But we are entirely missing the product. We have no idea what the equilibrium concentration of phosphorus pentachloride is.
So we have to isolate the unknown variable. Step 1 is the same. Write the expression.
Products over reactants. The numerator is just PCl5. The denominator is PCl3 times Cl2. So our equation is Kc equals PCl5 divided by the quantity PCl3 times Cl2.
But we can't just plug numbers in yet. We need PCl5 all by itself on one side of the equal sign. We have to rearrange the furniture.
Right now, PCl5 is being divided by the two reactants. To undo division, we use multiplication. We take the entire denominator of the PCl3 times Cl2 block and egg and multiply both sides of the equation by it.
Moving it from the bottom of the right side over to the left side where it multiplies directly against the Kc constant.
So our new rearranged formula is the concentration of PCl5 equals the Kc times the concentration of PCl3 times the concentration of Cl2. The messy fraction just turned into a clean, straight line of multiplication.
It's much cleaner. Now we feed the data into the rearranged formula.
Okay, we take our known Kc, which is 0.13, we multiply by our known PCl3, which is 10.0, and we multiply that by our known Cl2, which is 9.0.
10.0 times 9.0 is 90.
And 90 times 0.13 equals 11.7. So the missing equilibrium concentration of our product, phosphorus pentachloride, must be exactly 11.7.
The arithmetic is flawless. But I want to highlight something genuinely bizarre about a quirky detail in how the source text chooses to write out this final answer. This is a moment where rote textbook application crashes into physical reality. Look at the very last line of the solution for the scenario in our notes. What does it say?
Okay, looking at the text, it literally prints PCl5 equals 11.7 mole to the -1 decimeter cubed.
Stop right there. Think about what that implies based on everything we've established.
Well, earlier we definitively stated that square brackets mean concentration, and the universal unit for concentration is moles per cubic decimeter. It's a standard measure of density. But the text just attached the highly specific inverted unit of the Kc constant to a standard concentration value. Physically, that implies a negative amount of moles per volume, or an inverted volume space. That doesn't make any sense for a simple measure of density.
You've spotted a fascinating artifact of academic shorthand. The textbook isn't describing reality in that final line. It is blindly copy-pasting an algebraic remainder without finishing the dimensional analysis. They are strictly adhering to the units from the previous step without resolving them.
Wait, really? If you actually trace the units through the multiplication we just did, does it fix itself?
Let's do it right now. Our equation was Kc times concentration. The Kc unit was mole to the -1 decimeter cubed. We multiplied that by the first concentration unit, which is standard mole per decimeter cubed.
Let's pause there. The mole to the -1 from the Kc multiplies with the standard mole to the +1 from the concentration. They cancel each other out to 0, or algebraically they become 1, and the positive decimeter cubed cancels with a negative decimeter cubed.
Precisely. The unit of the constant and the unit of the first concentration perfectly annihilate each other.
Which means the only unit left standing is the unit from the second concentration term we multiplied by, the standard moles per cubic decimeter.
Exactly. If you rigorously execute the algebra, the inverted units vanish and the final answer emerges wearing the perfectly correct standard unit for concentration. But the author of the text took a shortcut. They skipped the unit cancellation step and simply slapped the constant's unique unit onto the final number.
That is such an incredible catch. It just proves that you cannot passively consume scientific texts. You have to actively interrogate every piece of data, right down to the superscript letters at the end of a math problem. I mean, we are using this text as our guide, but we can acknowledge that their specific arrangement of letters there is, well, it's a typographical hallucination.
That's a great way to put it. It shows you are holding the mathematical abstract accountable to the physical reality of the beaker.
Well, speaking of actively interrogating the math, to ensure you, the listener, have truly absorbed the rule of coefficients. I want to use the last part of our deep dive to really solidify these expressions. We're turning to the final exercises in the source. Test yourself 9.2.
I love these exercises. Question 4 asks to point out the coefficients, and question 5 asks to write the expressions for hypothetical and real reactions. It strips away the complex chemistry and leaves only the structural logic.
Let's run through a couple of these hypothetical models to test our mental models. They just use letters A, B, C, D to isolate the pure logic. The first hypothetical model equation is 2A plus 3B, reversible arrows, 4C plus 2D. Building the blueprint on the fly. Products on top. That's C and D. The coefficient for C is a massive 4, so it becomes C to the 4th power. The coefficient for D is 2, so it's D squared. The numerator is C to the 4th times D squared. Excellent. Now the reactants on the bottom, we have A and B. The coefficient for A is 2, so A squared. The coefficient for B is 3, so B cubed. The denominator is A squared times B cubed.
So the full architectural expression is KC equals C to the 4th times D squared, all divided by A squared times B cubed. Just visually it's striking. Imagine the sheer sensitivity of that fraction. You have terms being raised to the 4th power.
It really emphasizes how dramatically a tiny, microscopic change in concentration can violently swing the final equilibrium if it's being exponentially multiplied. I mean, a 1% increase in chemical C doesn't just bump the ratio 1%, it gets multiplied by itself 4 times.
Exactly. It creates a highly nonlinear system. Let's try another one. 4x goes to 2y plus 3z.
Products are y and z. Coefficient 2 for y becomes y squared. Coefficient 3 for z becomes z cubed. Numerator, y squared times z cubed. Reactant is just x, but it has a coefficient of 4, so the denominator is just x to the 4th. Full blueprint. Kc equals y squared times z cubed over x to the 4th.
Spot on. And the last hypothetical, 2m plus 4n goes to 5o.
Product is O. Coefficient is 5, so numerator is O to the 5th. Reactants are m and n. Coefficient 2 for m is m squared. Coefficient 4 for n is n to the 4th. Denominator is m squared times n to the 4th. Blueprint is Kc equals O to the 5th over m squared times n to the 4th.
You've mastered the translation. You see a number in the physical recipe and you instantly know how it warps the mathematical probability space. Let's apply this newly honed instinct to the final real-world gas reactions listed in our notes.
Okay, bringing it out of the abstract and back into reality. The first one is nitrogen dioxide turning into nitrogen tetroxide. The equation is 2NO2, reversible arrows, N2O4. The product is N2O4. No visible coefficient, so it's an implied one. Numerator is simply bracket N2O4 bracket. Reactant is NO2, and it has a coefficient of 2, so the denominator is NO2 squared. The expression is Kc equals N2O4 divided by NO2 squared.
Perfect. And the last real one, sulfur dioxide reacting with oxygen to form sulfur trioxide, 2SO2 plus O2 goes to 2SO3.
Product is SO3, coefficient of 2. Numerator is SO3 squared. Reactants are SO2 with a coefficient of 2 and O2 with an implied 1. Denominator is SO2 squared times O2, full expression. Kc equals SO3 squared divided by SO2 squared times O2.
Once you see the matrix, you can't unsee it. You are literally just translating the physical collision requirements into an algebraic format. It serves as a great rhythmic review of the core mechanic.
It is incredibly satisfying to think that the sheer, unimaginable chaos of a trillion molecules crashing into each other, forming and breaking apart in that murky soup of a reversible reaction can all be perfectly distilled down into one clean, elegant fraction.
It is the ultimate order hidden within the chaos.
Which really brings us to the end of our journey through this specific stack of notes. Let's summarize the core mechanics we've extracted today about chemical balance. We started by redefining Kc. It's not just a math problem, it is the ultimate scoreboard ratio of products to reactants.
Right, and we discovered that this ratio is heavily dictated by probability. The power of the coefficients exists because the physical recipe demands simultaneous collisions. That physical hurdle manifests as mathematical exponents.
We also dug into the golden rules, specifically the paradox of initial concentrations. We learned that while the formula is built out of varying concentration numbers, the final destination, the Kc value, is completely independent of your starting inventory. The system will forcefully shift, react, and strain to reach its designated ratio, whether you start with a thimble of reactants or a tanker truck full of them.
And we traced the unit gymnastics. We saw how the units are not just arbitrary labels, they're physical descriptors. They morph, square themselves, or invert entirely to tell the story of the spatial geometry and compression happening inside the reaction vessel.
But the absolute biggest takeaway, the core focal point we kept coming back to.
Let me definitively restate it. Temperature is the master switch. It is the single solitary key that can unlock and rewrite the value of an equilibrium constant. Because temperature changes the kinetic energy, it unequally impacts the forward and reverse speeds depending on their heat requirements. If you change the temperature, you establish a brand new mathematical destiny for the universe of that reaction.
That concept actually leads me directly to a final thought I want to leave with you, the listener. Something to mull over as you digest all this math and theory on your own.
The implications of this are massive, so I'm curious where you're going with this.
Well, we spent a significant amount of time talking about the Haber process today, the synthesis of ammonia.
Yeah.
N2 plus 3H2 makes 2NH3. In the real world, outside of textbook problems, ammonia is the bedrock of modern synthetic fertilizers. It quite literally feeds billions of people on this planet. Chemical engineers are tasked with making thousands of tons of this stuff as fast and as efficiently as possible.
Which is incredibly difficult because, as we've learned, the reaction is reversible. It hits equilibrium. It reaches a stalemate.
Exactly. Equilibrium is a factory manager's worst nightmare. The reaction naturally stops halfway, leaving massive amounts of precious, unreacted nitrogen and hydrogen just sitting idle in the tank, perfectly balanced with the ammonia.
A completely inefficient stalemate.
But we just learned the cheat code. We know that Kc dictates that frustrating balance, and we know that temperature is the only thing that can dictate the Kc. So imagine you are the lead chemical engineer at one of these massive industrial plants. You aren't in a lab. You're looking at 6-story tall pressure vessels. How might you actively manipulate the temperature in that plant to cheat nature? If the reaction forming ammonia is exothermic, meaning it releases heat, how could you use constant aggressive cooling or sudden thermal shocks to continuously shift the Kc value, keeping the system perpetually off balance, forcing it to yield almost entirely products instead of ever letting it settle into its natural halfway stalemate?
That is the multi-billion-dollar question. You are taking the abstract algebraic fraction we built today and using it to play God with industrial yields. You are actively weaponizing the temperature to rewrite the chemical destiny.
It's nature's ultimate puzzle, and learning the rules of the Kc fraction is the only way to solve it. Thank you so much for joining us on this highly detailed, mathematically intense, but hopefully rewarding deep dive into the hidden mechanics of chemical balance.
It was a true pleasure unpacking the chaos with you.
Until next time, keep questioning the formulas, look for the ratios hiding in the chaos, and we will see you on the next deep dive.